In this module, we will be looking at thermal comfort in built environment. To give you a quick overview, thermal comfort is something for which the whole effort is being made. You talk about climate responsive building, you are making it climatically responsive in order that internal environments are thermally comfortable. It includes provision of proper temperatures, appropriate temperatures, curtailing excess heat gains, minimizing heat losses, enhancing ventilation. So, it involves a series of phenomena by virtue of which you call something like overall thermal comfort inside the built environment. The contents would be an introduction for thermal comfort, then we will look at what are the factors actually contributing to thermal comfort, then we will go for comfort zone and thermal comfort models. Human body produces heat continuously, it is like a machine. We call it metabolic process. As a part of this process, there is a continuous heat generation which happens, because of which heat emission dissipation happens. The heat output varies somewhere between 70 watts during sleep, and if you are involved in heavy physical activity, it may go up to 700 watts. So, it depends primarily on what kind of activity you do. So, if you are in the class sitting and listening versus a faculty who is taking a class, you are working in an office versus you are on the street doing some physical activity or you are going for a jog, the amount of heat dissipation considerably varies from one to the other. So, if the environment, the ambient conditions indoor or outdoor, if it is amicable, then proper heat dissipation would happen. Whatever excess heat is generated will be dissipated to the environment. Moment the ambient conditions are not in terms where it can get this heat or it can absorb, it can become a heat sink, then the human body starts sweating, which means the excess heat is being given out in the form of sweat, and because of this evapotranspiration, then because of this evaporation, heat dissipation happens. So, this is something we will look at further in detail. We have two body temperatures, one is a core body temperature which is somewhere around 37 degrees, and the skin temperature, that is a surface skin temperature, which may range from 31 to 34 degrees centigrade. When these two things are in place, we are physically fit. When these go up or come down, then the body starts to adjust itself by either by sweating or by shivering in terms of heat or in terms of cold discomfort, that is what we mean. So, beyond that we get into the health related troubles. It can go up to a heat shock or frostbite on the other side. This is a metabolic heat balance or heat balance equation, commonly termed as, it is quite old derivation which is there. It is a very generally accepted broad outline of understanding how heat exchanges happen. Here there are different terms. First is the metabolic heat production that we talked about in the previous slide. The next is net radiation exchange which happens between a person and the environment. Then you have convection exchange which includes the respiration. So, whatever we breathe, we are also losing heat or gaining heat. Then you have the conduction exchange, again you can gain heat or lose heat if you are in touch. It can be the floor surface, or if you are reclining, if you are sitting, then there could be some amount of heat exchange. Then you have evaporation which again includes respiration. Then if you have this on the left hand side, on the right you will have the change in stored heat. If these things are not equating or negating each other, there will be some remainder which is delta S, that is change in the stored heat. If these things cancel each other, then this will be 0. If you look more closely into this, metabolic heat production is always possible, positive. You keep producing heat, there is no negative term here, so it is always heat gain, heat production. Net radiation can be positive or negative. You can gain heat through radiation or you can lose heat through radiation. Convection again plus or minus, you can gain heat through convection or you can also lose heat through convection. Conduction similarly is plus or minus, minimum amount of conduction happens, mainly it is radiation and convection. Wherever you are in touch physically with objects, then you will have conductive heat losses or gains. Then evaporation, finally it is a delta S, that is a net stored change in the net stored heat. If you take an ideal scenario when all these things negate each other, they cancel out, you get 0, which means there is thermal comfort. Ideally we should not be calling this as thermal comfort, but we must be using a term called thermal equilibrium. Our body is said to be in the state of thermal equilibrium with the ambient condition, indoor or outdoor conditions. But then what we talk about here is only the cognitive part, cognitive thermal sensation. This is what is primarily referred using this heat balance equation. If you read the definitions of thermal comfort in any standard, it is defined as the condition of mind which expresses satisfaction with the thermal environment. Here we are using two terms, expression and expression of satisfaction, and it is the condition of mind. So when you talk about the condition of mind and expression of satisfaction to the thermal environment, apart from this thermal equilibrium and cognitive thermal sensation, we have another term called thermal perception. So you have certain cues, your body is sensing it, cognitively it is sensing certain thermal condition and you are responding to it, and beyond this response you start perceiving thermal comfort. Here we come into two terms or two notions of thermal comfort. One is the physiological approach to thermal comfort, next is physio-psychological approach to thermal comfort. If you look purely at the heat balance model, thermal equilibrium and cognitive thermal sensation, then you can deal with it in terms of physiological approach. That is, you are talking about the core body temperature, skin temperature, ambient temperature, and how heat exchange happens between these three nodes. Or if you are talking about the second approach or the second notion, you come to terms with the thermal perception. The same environment you may be feeling, may be warm, I may be feeling it as comfortable, somebody may be feeling it as slightly more warmer than you feel. So it varies from person to person. There is a psychology. I may feel the same environment today as warm, eventually say after a week, after 2 weeks, I may feel this is okay, I may feel it is comfortable. So when you say thermal comfort, apart from physiological, you also get physio-psychological. We will look about this physio-psychological approach in the next, one of the future modules. First we will take a close look at what is thermal comfort, and physiologically how do you define heat balance and how do you define comfort by itself, what are the parameters. That is what we will look more closely into. What are the factors influencing thermal comfort? There are three different sets of factors in fact which contribute to thermal comfort. First is the environmental parameter, set of environmental parameters. Basic is air temperature, referred as dry bulb temperature technically. Air movement includes air velocity and the direction. Humidity, relative humidity, indirectly it refers to the amount of moisture or moisture content in the air. Then you have the radiation, that is the radiant exchanges are controlled by this. So 4 environmental variables, it can be outdoor or indoor. Then you have 4 personal variables. First is the metabolic rate, like we talked about earlier. Depending on the activity you perform, your heat generation varies. So the excess heat which needs to be dissipated considerably varies from one activity to the other activity. So based on this, metabolic rate is a primary determinant of the personal variables. Then next is the type of clothing you wear. What type of clothing? Is it a light summer clothing, cotton wear, or is it like a thermal wear which you put in the winter, a woolen cloth? Next is the state of health. We will look at these parameters more closely. Then the state of health, it varies from person to person. If you are okay physically, if you are not sick, then your thermal perception differs, whereas if you are with some ailment, you may perceive the same environment slightly in a different manner. Then comes acclimatization, which means adjusting to the thermal condition, set of thermal condition. It may be short term adjustment or long term adjustment. Say for example, within winter there is a sudden rise in temperature among the winter months, suddenly there is a temperature increase and then it again drops down. The winter is really chill. For example, you are dealing with say 8 degree, 10 degree temperature, average temperature during winter. Suddenly there is an increase, you get 25, 26 degrees and then it drops back. So the perception of the chillness considerably gets affected, but over a period of time, say within a short duration, say 3 to 4 days or maximum a week, you will get accustomed to. Similarly, a short spell of rain during summer, to bounce back to the regular adjustment you will need 3 to 4 days. You may feel slightly more hotter or cooler than you actually would have. Then there is a long term acclimatization. Imagine you are moving from a colder climate, a city in a colder climate like Srinagar, you are located in Srinagar, you are moving for a job to some other hotter location like Jaisalmer. For the first year, second year, you will eventually get acclimatized or adjusted, your psychology will get adjusted to this place, and after say 1 or 2 years, it varies from again person to person, age, gender, lot of variations are there. Because of that, you will eventually get adjusted to particular thermal environment, then your complaints of discomfort will eventually come down. Other factors which are contributing to it apart from these two depends on the food habits, the drink you take, body shape, the fat content, we call BMI and other height, weight things which are taken into consideration during thermal comfort assessment. Age and gender of course has a great contribution. Now as a part of this particular module and the next module, we will primarily look at the environmental variables and 2 personal variables which are primarily contributing to it. Immediately we are not discussing this, but in one of the later modules where we talk about thermal adaptation, adaptive thermal comfort, we will talk about little bit on acclimatization, age and gender, etc. First about air temperature, it determines the convective heat dissipation, how much effective the convective heat losses or gains happen is determined by the air temperature, that is one of the primary determinant of it. Next is air movement, it accelerates convection, it alters the skin and clothing surface heat transfer coefficient. Each surface has something called film coefficient or surface heat transfer coefficient, it is a total integrated factor of convective and radiative exchanges as well. So we will study more about heat transfer coefficient in one of the other modules. It alters the skin and clothing surface heat transfer coefficient, it has an impact of heat transfer through the clothing also. It increases the evaporation from skin. So these are the effects of air movement, higher the velocity, better the heat losses happen during summer. Humidity, when the humidity is really high, it is sultry, the air is getting saturated 90-95% humid or even more, it restricts the amount of evaporation that can happen. So because of which you will start feeling more uncomfortable. This is typically the happening which takes place in coastal areas or humid climate specifically. We will look at some examples. I am showing you few measured examples which were taken in residential environments. Climate conditions may vary, but in this case this is a hot and dry climate. Typically the measurements were taken in winter. I am just trying to present what happens with the indoor air temperature, air humidity and air velocity, how these things vary with respect to outdoor condition, just to give you a perception of what are we talking about, what kind of comfort or discomfort we are dealing with or talking about. Here in this axis you will find the hour, this is 3-day recording, 0, this is the first day, 24 hours, then second day starts, this is the third day. Outdoor temperature variation is a cyclic phenomena, the red dotted line indicates the ambient temperature, then there are 2 rooms here, one is a east exposed room, that is a blue color line, and the grey one is a west exposed room. So there are 2 lines which closely follows the ambient condition, the cycle of variation, the maxima, minima as well as the time of occurrence. Of course there is a delay, there is a slight amount of damping, slight damping which is available, but apart from this the trend is similar because this is a naturally ventilated residential space. 2 residences have been presented here, and the thin grey bars which you see in the background, you have to refer to the right hand axis, that is RH. This y axis is temperature, that is what I was talking about. The right hand y axis, here it is a relative humidity in percentage. So this also varies somewhere between 50-55% and minimum you can get around 35 to 40%. This is a hot and dry region of peak winter, it is not peak winter, it is just off peak winter, more or less moderate variations were observed. This is typically what you will see when you are looking at naturally ventilated residential conditions. And indoor air temperature considerably varies, as I said, with respect to east and west exposed spaces. Here this is another example which we took in a hot and humid climate, where the green is an east exposed space, red is a west exposed space. It may vary, again it is one such example, it may vary from case to case, there are other factors. So this is the effect of orientation, same material, everything is same, just the space type, everything is more or less the same, but by virtue of orientation there is a slight difference in the temperature, you get about 1.5 to 2 degrees temperature difference because of orientation. In a nicely cross ventilated space where 2 opposite facades have walls, have windows which is well ventilated, you may be able to expect somewhere around 0.2 to 0.3, or sometimes when it is really well ventilated you will get around 0.6, 0.7 meter per second air velocity through natural ventilation. Again It is not a consistent airflow that you can expect, so it may vary with time. This is a seashore, it's a coastal area, so you get, sometimes there is a good breeze, again it drops down, then again it increases. Apart from window modulations or balcony door modulations that you do, typically you can expect somewhere around 0.5 to 0.8 meter per second air velocity in a cross ventilated space. We talked about temperature, humidity and air velocity. The next important parameter which contributes is the radiation exchange. This is a very crucial factor in determining how comfortable or uncomfortable you are in a given space. We commonly refer the term called MRT or mean radiant temperature, which is one of the most commonly used indicator for the radiant environment or radiant thermal environment. Radiation exchanges can be set using this. It is nothing but average temperature of surrounding surface elements weighted by the solid angle and the area it subtends. So it is like how much area is exposed to me, or as a person, if I am put in the center of the room, how many surfaces are there and at what temperature they are and what angle they subtend. So this is primarily determining the radiant exchange between these surfaces and myself, when I am sitting in a particular room. As I move away from a surface or as I move close to the surface, my tilt angle varies, then the radiant temperature is considerably going to vary. One thing we must understand, MRT as a parameter is not directly measurable mostly. You actually determine it or derive it using another term called globe temperature. We measure it using globe thermometer. We studied this in school as well. The conventional way of measuring is keeping a thermometer, mercury thermometer, inside a copper globe. It's a matte black painted. It's like a perfect black body. It's like a heat sink. It absorbs all the radiation from various surfaces. You put this thermometer inside the copper globe. There is air temperature. First, this is measuring air temperature. Apart from this, it is also sensing the increase in temperature due to radiation exchanges. So the mercury gets heated up, you get slightly increased temperature if it is a warm environment. On the other hand, if you put the same globe in a really cold chamber, there is going to be heat loss. This is going to lose heat. This particular black surface will start losing heat and you will find a slight drop in the globe temperature. By using globe temperature, you will be able to determine mean radiant temperature. We will look at it how. A simple setup that we typically use for our measurements. We have a data logger here. This is a globe thermometer I was talking to you about. Instead of a plain thermometer, it has a sensor, temperature sensor inside this, but the principle of working remains the same. The white one, thin white one here is a temperature and humidity probe. This one is a hot wire anemometer. For indoor measurements, typically if your air velocities are less than 0.5 meter per second, vane anemometer, which is commonly used in laboratories, vane anemometers may not be much useful because their sensitivities might not be that low, because they do well for velocities around 1.5 meter per second or sometimes as low as 0.3 or 0.5 meter per second. But indoor air velocities, when you are trying to measure something like 0.1, 0.15, hot wire anemometers are more sensitive. They will be able to give you as low as 0.05 meter per second air velocity. Again, it depends on the instrument sensitivity. There are few other probes. This particular one captures the radiation from this side and this side. It determines what is the radiant difference between these two, radiant asymmetry we call. We will look at this shortly. Now I have measured globe temperature. Using that, there is a simple equation, a formula which has been in use for quite some years. With globe temperature, you add the air velocity component. This is square root of air velocity and the difference between the globe temperature and dry bulb temperature. So effectively, as I said, when the surfaces around you are cold than the ambient temperature, the globe temperature or MRT is going to come down than the average air temperature. Whereas if the surfaces are hot, then your mean radiant temperature would probably be higher than your air temperature. Classic example of this: imagine you are traveling in a car, you are in the front seat, you have the windshield, you are driving towards west in the evening, you have sun in front of you, sun is heating up the glass, you get radiant heat from the windshield side, whereas you are trying to cool your car down through your air conditioner, which is actually throwing cold air on you. So you have a convective heat loss and radiant heat gain. This will never tally with each other. Even if you put your AC in full blast, if the sun is really harsh, then you are still going to feel the heat of it, unless you have a very well conditioned system where you have throw from 3 to 4 directions, then you are kind of getting neutral with it. Otherwise the radiant heat exchange, heat gain will be more prominent and you will be still feeling uncomfortable. Typically in warm, another thing to note, it varies with respect to air velocity. As the velocity increases or decreases, MRT is going to go up or down accordingly. In warm climate, when you are with lighter clothing, the contribution of mean radiant temperature, say if you are perceiving some temperature, you are not going to actually perceive the air temperature, but in a warm climate when you are with light cotton wear, then what you actually perceive is only 1/3 of dry bulb temperature and 2/3 of mean radiant temperature. Imagine your ambient dry bulb temperature is 30 degrees, but your mean radiant temperature is 40 degrees. Then you will still be uncomfortable, because even 30 degrees as such 30 is okay, but when the radiant temperature is increasing, 2/3 of contribution is made by this, so you are going to feel uncomfortable. Similarly in cold climate, when you are with heavier clothing, say woolen wear, the perceived environmental temperature is half of mean radiant temperature and half of dry bulb temperature. This is also partly due to the amount of surface, body surface, which is exposed to ambient. Here what happens with lighter clothing, much of the body is exposed to the ambient surfaces around you. So there is more probability of heat gains from these surfaces. So MRT takes the front seat, whereas here you have more or less covered yourself, as well as the surface properties are different. You are in heavier clothing, as well as it is a colder season, then it is half contribution, but still you will have half of the contribution made by mean radiant temperature. If the surface is really cold, you will still be feeling uncomfortable. We have been always talking about an ideal imaginary room. Place yourself in the center, you have 6 surfaces exchanging heat with your body. It either contributes to heat gain or heat losses through radiation, but ideally in an actual condition what happens, there are n number of surfaces, you have tilted different angles, different amount of surfaces. Say even a bookshelf, you have the solid wooden or metal surface, then you have books, you have window, frame, glass, lot of other things are there, everything is getting involved in the total heat exchange. So effectively determining mean radiant temperature in actual case is really a challenging activity. I am giving you similar examples of few mean radiant temperature measurements. This is from an unexposed roof condition, this is the topmost floor in an apartment. 3 cities we measured. More or less the indoor conditions, that is the spatial typologies were similar, the floor area plus the orientation were more or less kept similar. 3 different cities, just to give an example of how mean radiant temperature varies. This is the case of Bangalore, Hyderabad, the peak comes close to, this is the Chennai line, so this comes close to this. It may vary from case to case, of course, orientation, lot of other parameters are there, but typical variation, and this is how it relates to the indoor air temperature. It more or less revolves around indoor air temperature. You will also observe similar pattern of variation, but in hotter conditions, hotter climate, it might slightly go up above the air temperature during the peak time when there is a good radiant exchange. Say if you are in a room with large glazed window surfaces or balcony doors, then your MRT is going to really shoot up, but then it will also drop eventually. In the night it will get really cold. Then it more or less follows the pattern, but the magnitude of difference might depend on various aspects, like including orientation, depending on the glazing, glass surface area, radiant property of surfaces, the magnitude of variation might differ from one another. Similarly, the variation in globe temperature or mean radiant temperature, you have a good amount of variation in terms of roof exposed versus roof unexposed condition. Lot of us have an apprehension that the topmost floor in a flat has more amount of thermal discomfort. You generally do not prefer buying a flat just on the topmost floor, for one reason that you get a lot of heat. We know that we get a lot of heat, but it is not just the heat gained through the surface, but it also raises the mean radiant temperature. Probably if you are putting air temperature sensor in 2 flats, one in the topmost floor and somewhere in the lower floor, air temperature is more or less going to be similar, maybe half a degree difference you may be able to find, but moment you put a globe thermometer, you start measuring globe temperature and calculate MRT with it, you are going to find a considerable amount of difference, 2 to 3 degrees easily you can find even with a properly treated roof. Let us talk about personal factors. First is the metabolic rate. We talked about watt or watts per meter square of body surface. This is typically a scientific measure, but as per thermal calculation we are trying to simplify it we are trying to use a term called MET, MET. 1 MET is equal to 58.15 or 58.2 watts per meter square of heat emission. This is like equivalent to body surface of a normal adult is around 1.7 meter square. If you take a sitting person doing sedentary activity, say you are in an office or you are in a classroom, you are listening to something, you are doing typical office work, computer based work, you will have a heat loss of around 100 watts. So effectively the MET value will be around 1.5, 1.6. Again it will increase, say if you are sleeping it will be 0.8 MET, if you are sitting it will be close to 1 MET, playing, jogging, each one has a different metabolic activity. So the average activity level varies for each of these activity. Just a quick hint, if you are really trying to estimate the thermal comfort of a person, it is not the momentary activity that you have to be taking care of. Say for example, if you were to ask this guy who is sitting here how comfortable you are feeling or how uncomfortable you are feeling, we might be missing a critical link. He might have just completed a jog and he might have been sitting here. So the perception is different for this guy versus this guy. So ideally what we generally, what we do for our comfort surveys or comfort assessment is we take into account what this guy or this lady did for the last 1 hour, what kind of activity they were performing and what is the amount of heat emission, what is the MET value during the last 1 hour is always accounted in thermal comfort calculation. The next factor is the clothing insulation, what kind of clothing you wear and what is the thermal resistance the clothing offers. So actually the clothing is one kind of capsule that protects you from the outdoor environment. This is one line of protection. The thicker or the more insulative your clothing is, the lesser the heat exchanges that would happen. This is typically what happens during winter. You have a thermal wear, you have a woolen which prevents heat exchange from, rather heat loss from the body to the ambient. Similarly during summer you have a thin cotton wear which enhances the convective heat flow to happen between the ambient and the body. So the clothing insulation typically it is a resistance value meter square degree centigrade per watt, but here again to simplify this we will refer to it as a term called CLO, CLO. 1 CLO is equal to 0.155 meter square degree centigrade per watt. Typically we can refer it as 1 CLO. It depends from clothing type to clothing type. For example, this would be around 0.3 or 0.4, whereas a typical office wear could be around 1.5 CLO value. It depends on the type of insulation, the material used. There is a lot of research happening around on different type of ethnic wears and what is their clothing insulation, which we did not have in our repository. The last few years there has been a lot of interest where people are trying to find out different type of clothing and what is their actual insulation. This has a good amount of role being played in terms of the perceived thermal comfort. So we will stop this module here. We looked at basics of thermal comfort and we looked at environmental and personal factors influencing thermal comfort. We talked about 4 environmental parameters: air temperature, humidity, air velocity and radiation, and 2 personal factors, metabolic activity and clothing insulation, and how they influence thermal comfort. Thank you.